Uh, Good afternoon, dear members, industry colleagues, and good morning and good afternoon to our speakers from both Germany and India. A hearty welcome to all of you today for the VDMA Robotomation Technology Update Robot Vision Trends being organized by VDMA Robotic and Automation Division in cooperation with VDMA India. We hope all of you and your family and colleagues are safe and doing well. I'm Jamli John, based out of the Mumbai office of VDMA, and I'll be taking you through the session. Before we continue, we'll request all of you to kindly keep your microphones muted and cameras switched off. You could continue to post your questions to us in the chat box section, and we'll be taking it up during the last leg of the web seminar. Next slide. VDMA, the Mechanical Engineering Industry Association, was founded in November 1892 and is the most important voice for the mechanical engineering industry. VDMA represents around 3,300, mostly medium-sized companies, making it the largest industry association in Europe. The members were currently contributing to 78% as exports, which is equivalent to 232 billion euro production. Recognizing the very early significance of India as a future market for our member companies, India was one of the first overseas offices among the BRIC countries. VDMA stands to be the only German industrial association having well-established offices in India since several years, with our presence currently being in Noida, Kolkata, Mumbai, and Bangalore. Next slide. For today's web seminar, we will have the welcome address from Mr. Rajesh Nath, Managing Director of VDMA India, and this will be followed by the Robotic and Automation Market Overview by Ms. Anna Wendel, Director from VDMA Robotic and Automation Machine Vision. Our technical presentations would be beginning with a practical overview about different aspects of modern robot vision solutions by Dr. Michael Kleinkes, Managing Director of BMT Machine Vision Technique, GmbH. Our second presentation would be on robotics for inline inspection and metrology by Mr. Michael Scheffer, Sales Development Manager, APAC, Car Body Solutions, Automated Inspection from Zeiss Industrial Quality Solutions, and Mr. Uday Dikshit, Product Sales Manager for Industry Quality, Carl Zeiss India. And our last presentation would be on collaborative robots enabled with 3D vision for inspection applications by Mr. Peter Weiklund, Senior Business Development Manager, LMI Technologies, GmbH, and Mr. Pawan Raikar, Technical Manager, Geoinformatics Consultants Private Limited. We will conclude with the Q&A session, and with no further delay, I'd like to hand it over to you, Mr. Nath.
Right. Good afternoon, friends, and all the members and industry friends who have joined us for this afternoon for a very relevant topic for the manufacturing industry, robot vision trends, being organized by VDMA India in association with VDMA Robotics and Automation Division. I extend a welcome to my colleague, Ms. Anna Wendel, and our speakers from Germany and India from the companies VMT Vision, Carl Zeiss, and LMI Technology. So hearty welcome to all our speakers and Anna. Thank you for joining us today for this webinar. Friends, technology has advanced so much that it has changed the way we manufacture. Developments in different areas, including robotics, collaborative automation, and industrial vision, have opened up many new capabilities for us. This has allowed automation to be applied to all production environments for both high and low volumes. There are many benefits of machine vision in automation. Machine vision inspection is widely recognized as a key technology for the automation of production lines. The adoption of inline inspection reduces the cost of production, increases customer satisfaction, and reduces waste. It is the key to product and batch integrity as well as batch mix prevention. By employing a vision inspection system in the early production stages, defective parts are immediately removed from the process. Faulty products never continue to subsequent manufacturing stages and therefore incur no further costs. In fact, defect products can be reintroduced back to the production process at a later stage. Though analysis problems can be rectified at the point of origin, resulting in increased system productivity and availability. Machine vision technology is unique in its ability to enhance quality, whilst simultaneously cutting costs and protecting the brand from recalls, fines, as well as adverse publicity. Industrial robots are already used extensively, and with the emergence of collaborative robots and rapid developments in 3D image processing, they are being used much more in combination, particularly for vision-guided robots. The vision system identifies the precise location of the object, and these coordinates are transferred to the robot. Massive strides in vision robot interfaces make the process much easier. Add to this the requirement for compliance-based inspection system conforming to the highest industry standards, and the selection of a vision partner who can provide a reliable turnkey vision solution has become more important than ever. Friends, machine vision systems have a huge range of talents. They check quality, guide machines, control processes, identify components, read codes, and supply valuable data on optimizing production. All this helps to automate robots reliably, safely, and precisely, thus improving their overall performance. In this web seminar today, our member companies, Carl Zeiss, VMT Vision, and LMI Technologies will highlight some technological updates and will demonstrate the contribution robotics paired with machine vision can make to an efficient production. However, before that, I would like to welcome and invite my colleague, Ms. Anna Wendel, for her presentation on market overview of robot and automation industry. Thanks for joining us, Anna, and over to you.
Thank you, Rajesh. It's a pleasure to be here, as always. To be honest, I would have preferred to travel to India to meet you all in person, as we did in the last two Robotomation symposiums, but unfortunately that is not possible. But nevertheless, I'm happy to be here, and as always, it's exciting to get a bit more about the Indian spirit. So thank you for the invitation. Yeah, I will give a robotics and automation market overview. But before I start, I would like to introduce a little bit what is robotics and automation. How do we, the VDMA, understand it? The next slide, please. Next slide, please. Rajesh already explained the three subsectors of VDMA, robotics and automation. It's machine vision, so when machines see and comprehend. And it's about robotics, so that's a huge innovation driver and core element of automation. And last but not least, the third subsector of robotics automation, we have integrated assembly solutions. So out of millions of components, the integrated assembly solution providers, they generate new products every day. And today, as Rajesh mentioned, we are going to get a technology update about robot vision. So robotics in combination, as you will see, it's an unbeatable team. But first of all, let us start with a small market update. Where do we stand with regards to robotics and with regards to machine vision? So next slide, please. As you can see here, that's the newest figures from the International Federation of Robotics, the IFR, and I can use them thanks to my colleague who runs the statistics. As you can see, 2018, 2019, we had a dip, but that's not surprisingly. Well, yeah, that's not so surprising given the COVID-19 situation. But overall, as you can see, growth. So new installations have more than tripled if you compare 2010 to 2020. So 2020, as I mentioned, minus 2% due to COVID-19. But as I can tell you, it's not as bad as in other industries and other sectors of the machinery industry. So looking at the customer industries, next slide, please. Industrial robots can be found everywhere. So all major industries rely on robotics, be it in food and beverage, in plastics, chemical, metal, machinery industry. So robotics and automation is globally on a high growth path. So 2020, something happened. So electronics surpassed automotive as largest customer. So electronics had plus 17% in new installations in 2020. Automotive, as we all know, the automotive industry is undergoing transferring and transforming periods. So we had minus 21 in automotive. But in all the other industries, be it food or be it plastics, we had an increase. Next slide, please. Looking now at robot installations in India. So thanks to the International Federation, we have these figures, so we can see how has the Indian market developed. So looking at the annual installations in 2020, again, more than 3,200 industrial robots were newly installed in India. Hence, again, an increase in the operational stock of industrial robots. So looking at the operational stock, that means how many robots are working in factories in India. So looking at these figures, next slide, please. That's not the slide I wanted to see, but nevertheless, operational stock, I hope you believe me, has been increasing over the last years. So according to the IFR, by end of the calendar year 2019, we had more than 26,000 robots working in factories in India. And if we look at the customer industries, the new installations in 2020, 744 units were installed in automotive, metal and machinery, 337 units, and electronics and food saw an increase in 2020. Thank you. Next slide, please. Unfortunately, we don't have figures about robotics and automation, about machine vision industry in India or worldwide figures. However, I can share with you how the German machine vision industry has been developing. Next slide, please. Next slide, please. Go to the again, the slide is missing. I'm sorry for that, but I hope you believe me that machine vision industry in Germany has been developing greatly. So it's a real growth market. So it has been reporting high growth numbers and record sales figures for years. Between 2013 and 2019, sales in the German industry grew by an average of 9% per year. And 2020, we saw a dip in sales of machine vision industry, but it was not as bad as in other industries. And the reason for the boom, I mean, if you see, sales have been more than doubled in the last 10 years in machine vision. So the reason for the boom is, well, equipped with machine vision systems, machines and robots are learning to see and to understand. And within the global race towards greater automation, machine vision is a key technology, which is not just found in traditional industrial sectors, but it's conquering brand new areas too. I mean, looking at our mobile phones, yeah, you have vision technology integrated. And by today, we are looking at robot vision. And I'm looking forward now to learn more about the technological trends. And next slide, please. The last slide now, please. So if you would like to learn more about machine vision, I would like to ask you to download our brochure. The link is provided here, and I will share the slides with you with all the graphs that I wanted to show, so sorry for that. And I'm looking now forward to learn more about a major trend in both industries, in the robotics and machine vision industry, that we have been observing in the last years. So it's robot vision, and therefore I'm not keeping more of the time. I'm very happy to hand over now to our member companies to get an update. So hello, VMT, Pebble and Fuchs. Hello, Thais, and as well, hello, LMI Technologies. So thank you.
Thank you, Mr. Nath, and thank you, Anna. The slides which are being presented by Anna and which will be presented by the other speakers would be shared after the web seminar with all of you. So do not worry if anything was missing, you'll receive all the slides. We'd like to now invite Dr. Michael Klenkes from VMT for his presentation on a practical overview about different aspects of modern robot solutions. Over to you, Dr. Klenkes.
Thanks a lot, Jenny. Thanks a lot, Anna. Heartily welcome to everyone here in this round. Just imagine we were sitting in a physical room, then 174 people in the auditorium would be looking to the stage where we poor guys are presenting our topics here, and that's an honor, that's fun. Thank you for the opportunity. My name is Michael Klenkes, working as a CEO of a great vision technology company consisting of 142 persons worldwide, acting in the company family of Pebble and Fuchs with more than 5,000 people all over the world. I want to give you an overview. That is the title of the presentation that I hope you see in the first slide. Could someone please give me a smoke sign that everything is visible? Thanks.
It's visible.
I saw your
visible.
It's great. Cool. So you see the title. I try to adapt here my window. That's kind of strange here working, but you should see it. So what do we want to do in the next 20 minutes? 20 minutes is not a lot of time, and an overview is always consuming a lot of time because you want to see everything. And the motivation for today is to give you certain pieces of vision technology, of different aspects, different solution possibilities that we do, that the market is doing, what is en vogue, and to give you a way of think further, to dive into it later, and just taking as an overview. We are not going into nitty-gritty technical details, but we want to see some pictures, how stuff is working, how you can transfer these ideas of technology solution to your tasks, your demands that you have with your customers or in your facilities. If that is okay, we jump into it. We dive into it. I tried to switch the slide. Yeah, it's working. We want to do 4 different scenarios, 4 different parts of robot vision in different dimensions. We will talk about pose recognition. So how to find objects in space to adapt the robot to a moving path along the object. We want to talk about how to get stuff out of boxes without any collisions. We want to talk about how to guide a robot along a part which is not 100% the same position and shape. So what happens if your parts have different shapes, but your robot path is programmed, but you want to adapt it to the current shape and moving path? And we want to dive into a huge topic about robot inspection, and especially talking about 3D inspection. How can we use robot vision solutions to inspect parts? And that is the overview. And now we go into it and we talk about pose recognition. So assuming you have a robot cell, you have a sports car and whatever object, please, these examples are automotive because VMT is doing 80% of automotive vision solutions. We do 10 to 15% medical solutions and 5 to 10% general industry solutions. So most of the examples are automotive, but you can transfer it to any other solution or object that you have. So we have a nominal position, there's a part. We have a multi-camera system, 3D pose recognition, uses a several number of cameras, let's say 4 in the edges of the robot cell, to create photos of an object, to calculate from the photos using markers in the picture, we will see that later, and mathematical algorithm to calculate the current position of an object which is meant to be the same all the time. So taking this red sports car, don't want to talk about a Ford Mustang here, but it is one. So this is in the nominal position and you did all the robot programming. Everything is working fine with your first car. We call it the golden car. And your application path is fine. Next car comes into your robot cell, and this car, due to conveyor effects, will not be in the same position. And we have to distinguish here, we are talking about a pose. So a pose means X, Y, and Z, Cartesian position and additional an orientation change. And that is very crucial. So if the second car is not in the same pose than the first golden car, your robot program without any corrections will just be applied like you see in the middle, real position, the same robot path on the gray car. The robot still thinks the world is okay and will move completely wrong. And what you want to do is you want to find these objects, so basic pose recognition in space in 6 degrees of freedom, and you want to send that to the robot with an, we call that work object transformation. So you shift the complete world of the robot to the new real position. You make a robot frame correction and the application is going smoothly and perfectly on the same place at the object in space where you want to have it. That's a basic idea. That is common technology, but there are details in it where some elements are very important. And here for you an overview how the system is generally working. So we are using a picture. Most of the times it is a grayscale image, and you see it in the big picture on the left side. That is an underbody of a car holded by a fixture, and usually you use holes or anything like that which has a good contrast, and you use these geometric markers to find the position of the car in space. You can do that in a CAD-based simulation. That is something which is going out of the commodity product which is existing since many years on the market, 60 pose recognition, into virtual commissioning, CAD-based simulation. Thus the next car, the next object which you're planning, which you don't product right now, is fitting the current cell, the current solution, and how much can you do in the office and just load and update when you're on site to get everything running in a very limited amount of time. And what you see here on the window is that is a software which is showing these image processing algorithms, lights, cameras which are mounted, and here you see a demo application which we did for a truck manufacturer, where sealing application, as you see, it has to be applied very accurately at the object, and this pose recognition has to be done to find the object in space to really hit with an accuracy of a millimeter or even less than a millimeter exactly the right position. And you can see that's a practically running system. From this kind of systems, we've got 1,000 and more running worldwide to do pose recognition. So that's the first easy, let's say, solution approach for modern vision technology. Now we go one step further, bin picking. If you go to Wikipedia and you type in bin picking, there are some keywords popping out of it. It means computer vision, robotics, end effector, poses, grippers, and all that good stuff. It is still a huge complex problem, and the theory means just take a robot, take your bin, take your parts, use a plug and play software, put a sensor on it, and there you go. That is not the reality that we experienced. There are certain levels of problems. If you have very easy parts, very good lighting, everything is like planned in theory, easy to do, but have a look on that. That are parts for a German manufacturer of cars, and it is glossy, shiny, it is chaotic. These parts are in every possible orientation. If you want to grip them magnetically, they stick together and you don't get them out of the box without any collisions, and that is bin picking. Bin picking is not taking a sensor, taking a plug and play software and good luck. Bin picking is a various field of different elements, and that is my key message for this part of the presentation. It means you have to deal with a robot, you have to create a good gripper which fits in the box and fits to the software, and you have to establish your interfaces to your PLC, to your safety environment. You have to make a good cell layout that you have enough space, room for the robot to move properly, to get all the parts out of the box. And at the end of the day, you need a software which is stable and easy to use. So you want to have a holistic solution. You want to have a partner which is giving you enough support that the package, robot, software, sensor, and everything around it is fitting together. Every time when we saw customers in the field who are doing patchwork solutions with plug and play components, in many cases they run into brick walls at a very late moment where it was very difficult to change the setup at that point. So our holistic approach and our goal is take the stability of the bin picking system at an overall focus. The system has to run steadily, constantly, without any collisions. And all the software which we built around that systems has exactly this focus. And to give you a small insight how we did that bin picking, that is a lab setup with a very easy sucking gripper. You can see there was a 3D fit, and what you see now is a very crucial part. Taking a part out of the box and put it into this fitting element, which has a play of 0.5 mil, is a very delicate task, because most of the time the gripping process itself is not that accurate that you can put the part down with that accuracy that you see here in the video. And that is one part where these bin picking solutions get very complex, and a good software package, software platform is needed to run a bin picking system properly. What you maybe see, there's a rotating laser over the bin. So the sensor in these solutions is also an element which is deciding about success or no success. You need a good resolution, you need a good light reflection and robustness relation in your sensor. You are not helped if your conditions about lighting from your surrounding is very bad and your sensor can't deal with that, so that you are not able to fit, like you see here in the window, fit the CAD into the point cloud that you get out of a 3D point cloud sensor to do this kind of bin picking. So jumping to different areas of bin picking, starting in the upper right corner, there you see the bin. So the CAD simulated bin, just consisting of geometrical elements like walls. So very easy put into CAD to cut off out of the 3D point cloud data where your points of interest are. You see in the colored point cloud, that is a real scan of the box, different parts that you saw in the video, and modeled CAD of the gripper in a gripping point of a part which is matched into the point cloud. And that is exactly what you want to do. The goal is find gripping points which are easy with no collision to get the part out of the box. Getting into it is one part of the point. The other part is getting the part that you grip out of the box. You see that in the down right edge of the slide, geometry simulation. Sometimes the way out with the part in the gripper is a very delicate one. You don't want to lose it, you don't want to damage. And in the really down right edge, you see deformation detection is a huge game changer. Most of the bins are dented, so damaged in some kind of way. And you want to select the perfect gripping points. For that, down left edge of the slide, you need a good gripper design and a software which is able to use the CAD file of the gripper to simulate your complete gripping process. And top left edge, CAD part integration. You want to be able to include your CAD file of the parts to pick into your software system to create the gripping points that you see in the middle of the slide, several gripping points on the part, to commission a system which is then possible to running stably over weeks and months without any human interaction to repair it or to readjust it. That is the basic approach of bin picking systems. That are several points that I want to give to you. If you think about bin picking, don't think about, can I see the bin and do I have a robot and that's it? It is a huge and multilateral, multifaceted topic that you should consider. Last slide, how our bin picking systems set up today. We're using an industrial computer in IPC that we connect to whatever sensor we find possible and adequate to use for a certain kind of demand. So we can choose out of different portfolios of different vendors on the market. And you can use that robot like you see on the right picture with a sensor in hand to move. You can fix the sensor in a steady setup next to the bin, over the bin, that you have a scan of the environment in your bin, and you communicate with the robot and the industrial PC over common interfaces with a robot tech package that we developed to get everything smoothly together and to build up your standardized but individual solution for your demands. That is always the equilibrium that we try to achieve. On the one side, every single problem, every single customer is unique, so unique solutions are preferred. On the other side, you want to approach to standardized solutions in vision applications to drop price, to get synergy effects, and that is the equilibrium that we reach, finding the best level between individual solution and standardized product. Good. That is a look into a software. What means software? For us, software means a common platform for everything you want to do. We have got two platforms where we do all our applications from inspection to bin picking. You always see the same software. And other elements that we do always are coming back to the tool set which is given by this platform. We call it multi-sensor systems. Later you will see the VMT-IS intelligence software, where we integrate our interfaces, our sensor data, and all the algorithms you see here. On the right side, you see the simulations, you see a 3D scan of the bin, and you see our filter graph element where you can plug and play boxes to configure your control plans with all the results on the left side. Basic platform, one-time software learning, different solutions with the same software platform. That makes it easy to change between different applications and still resting on the same platform, like you use on a Windows system in Excel, and on the same time you're using Outlook and other softwares. The platform is always the same. Jumping to the third of four topics, inspection is something really huge. I would need several hours to explain to you the different elements of inspections that we do. And here I roughly scratch the surface to give you a glimpse into what we do and what modern vision, robot vision is doing on the market. So this is one practical example, and that is also a motivation here, practical pictures, practical link that you can see how stuff is working. You see on the right side, that is a door, a car door equipped with all that stuff which is in modern cars mounted on the door. And the task is to find, is everything there? Is that okay? Or is something missing here? And what we do there is, this is the second platform that we're using. We take pictures and we elaborate these pictures with taught in templates that you can put into the software. We can measure distances, sizes, diameters. We can check positions in relation to the picture. Is it on the right position or is it shifted a little bit? We can read data matrix or barcodes. So all different tasks that you have to inspect a complex element. Detect colors is also possible. You don't have to work with grayscale images, but in most of the examples, grayscale cameras are used. So this is the classic approach, inspection. Here, a different example, but the same usage. It is a motor store of the company Steel, and here you see on the right side in the software where we have the different camera views. So that are the picture snippets that you can configure. It is not needed to program with our software. It is only needed to set the parameters and define what you want to do. On the right side, you see the online protocol where all measurements are stored and you can repeat them and save them and taking history functions and all that good stuff. And that is the second example of the classic 2D based, camera based inspection of parts. Now we are diving into the three-dimensional world. And imagine you've got a very complex part like this one, a 6-cylinder motor equipped with several complex stuff, yellow caps, tubes, elastic wires, turbochargers, pumps, whatever you can imagine. And the task is, say, is it complete? Is it good? Or does it have to be repaired or whatever? And the first slide, and we are stepping to several steps now, is a human view. We as a human, we look at that object and we see, oh, that's complex, but we kind of understand it. And with some experience, we could say, okay, one yellow cap is missing on the left down part. But what if you want to automate it? So let's take a grayscale camera, classic inspection grayscale camera. Looks nearly the same, but with a completely different approach. Now we still have a picture, but we as humans, we have got two cameras, a left and a right one. Some of us only have one eye, but most of us have two eyes. So we are equipped naturally with stereo vision, and we are equipped naturally with a huge brain capacity to process what we see. If you go to 2D camera vision, now you have a grayscale picture, and now you start to process what you see and teach in what is needed. That can be very, very complex. And for example, to find these errors, top left, not clipped in plastic tube. In the middle on the top, not really snatched in connector. So problems which are difficult to see in a picture, let me say impossible to see. And now we dive into the 3D world. If we use a 3D point cloud sensor and we take a snapshot of this object, and let's say the first object, which is perfect, which is controlled, with a lot of time, patience, and love, we check this part about the completeness and everything is fine. This is a golden reference, and the next 200 parts should be looking like this one. You can take a 3D picture, a point cloud like you see here, and for the next part, you do the same. This is the next part, looking nearly the same like the first one. And now we bring these two 3D point clouds together. We match them, and then we see where do they change in their geometrical size. Where do we have deviations? And that is exactly what you see here. Green means that's perfect congruent matching. Everything is the same size. But as soon as it gets more red, there's more deviation in geometry. And here, cut out the areas where we see, oh my God, there are geometrical changings. And that are exactly the points where we want to inspect the part and the errors that we want to see. And this example is not very intuitive to get because I can't rotate it right now. And you still see a 2D image because you're sitting in front of a monitor. But let's take another one, a turbocharger, same problem, 3D inspection. And when you begin to rotate the part a little bit, and I hope that you see the rotation because of the bandwidth and the presentation here, then you get an impression how 3D works and how you can highlight areas which are not perfect and which are the result of a complex 3D inspection here. That was chapter 3. Jumping into chapter 4, the last chapter, and then I will finish. We need 5 minutes and we are through. Robot guidance. What if a part comes into your robot cell which has a deforming, which is not always the same size, which can be in a different pose, like the 3D pose recognition we earlier talked about, but also can be bended and deformed in its size. And you have a very delicate application here as an example, upright edge. That is a ham flange ceiling. So you want to apply a sealing material while the doors are closed. So you have this kind of a hook needle, and you go into the gaps of the car, for example, between the front and the the back door on the passenger side, what you see here, and you put the needle in, and then you turn it by 90 degrees, and then you start to apply the sealing mask while the doors are closed. You can imagine if the door is in the wrong position, that will be bad because you can't get the needle into it. And if the door is not in the same shape, at some point you will scratch the nozzle and you will break it. And that is then one of the example demands that I want to show you here. Imagine you have got 6 different program points of your robot program. Left side in red, you want to apply the left and the down part of the door. And in the middle, you see a door, which is A, in a different pose, and B, in a different shape. It is a very, very bad paint manufacturing picture that I did last night, but that is kind of an example for a possible bending. Too bad, but it is an example here. So what you have here is a two-way problem. The pose is one side, and you can adapt your robot by a base frame transformation to the new pose, as we saw earlier, but that doesn't solve problem B, the bending, the different shape of the door. But you see on the right side, what you can do with a product we call BK. So it's our path correction software, where we use a robot using a laser sensor, coming to that later, to make measurements on the part, to find the deforming and adapt dynamically for every part the robot path without reprogramming. You are using the standard program path, but the robot itself will get correction values from the software to apply, like the green line you see on the right side. So different pose and different shape. And here you see it. What we use, for example, is a Pepper and Fuchs line runner sensor. So classical laser triangulation sensor. We also can adapt sensors from different manufacturers. That doesn't play a role here. And these sensors are taking laser cut measurements, like you see on the left side on the display, different measurements which you can put together like you want it. The number, how much you want it, how many you want it, and the configuration where your certain important points on the parts are to correct the robot program path. And with that tool, you're perfectly able to act agile on every part deforming that comes up into your production process. Look at this. It is a video which doesn't start here. It is a video where the front hood of a car, it deforms with every car, is measured now. That is the measurement process. It's very fast, pack, 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 pack. Just single shots of laser line measurements. And now there's the application. You see the nozzle is perfectly going along the hood. And each hood has a different deforming. And 1 millimeter is a lot in that process. Then you begin to scratch the nozzle, and then you begin to increase the risk that you break it and that you stop your process. Breaking is not the main problem. Stopping the process is the main problem. So last slide for today, everything in one platform. Here you see different applications, from bin picking, down right corner of the result window, from inspection down left corner, from 3D completeness check, geometrical check, top left corner, up to top right corner, comparison between the real and the CAD virtual part to say how is the quality of the part. All the applications in one toolbox, right side measurement protocol, history, statistic, predictive maintenance, left side all the details about the result. Top part, you can configure your results and configure the software to have one tool which is able to solve all your application needs. 20 minutes was the goal. 20 minutes were done. I'm thanking you from my heart for your attention. Opening up for questions later. I'm not sure how that is organized. Use this data matrix code. Just take your mobile phone right now, open your camera, hold it to the data matrix code, and your phone will enter all my contact details in your phone book and So we are connected, no need of writing emails or typing it in. Just use the auto mode here, and thanks a lot for your attention.
Thank you, Dr. Klankers. I think quite in detail, and I'm sure people will connect with you shortly. I'd like to now invite Mr. Michael Scheffler and Mr. Uday Dixit from Carl Zeiss for their presentation on robotics for inline inspection and metrology. Over to you.
Okay, now I'm expecting normally the intro video. Do you see the right screen? I'm not sure currently.
Yeah, we see the presentation, but you should switch to slide mode, Mr. Scheffler.
It's not in presentation mode at the moment.
Okay. Now it's. Can you just start again the sharing that I can wait? I have. Oh. I'm sorry. I'm still. Okay.
Yeah.
Sorry for waiting. This should now be the right modus. Yeah.
Yeah.
So,
now it's fine. Yeah.
Thanks a lot. Yeah. So we have seen very nice samples in the presentation before for bin picking, part recognition, part position recognition, and also inspection. And I will go together with my colleague Uday Dixit from India a little bit more into the direction of robotics for inline inspection and metrology. Yeah. And so as we are short in time, I will already show you the first slide. What we are seeing here is a somehow symbolized representative automobile production site. And we see different areas with different requirements for quality assurance. Yeah. So we have, for example, the tooling, we have the press shop, we have the parts production in the body shop, serial analysis, measuring center, body shop, paint shop, and assembly. And you can, how to say, imagine that in all these areas, we have really different, how to say, requirements. And this you can, of course, not solve with one single sensor. And so what I want to show here is, let's say, therefore, we need a certain, how to say, construction kit or a tool kit of different sensors which can be applied on robotics for those different applications. So we have, for example, an IMAX sensor which will show an application for feature measurement, also cloud sensors. We will show you some IMAX twin sensors which are for the application of flush and gap measurement, ISIL trace where we can also do correlation-free inline metrology. And you see, let's say we need really here different strategies for different manufacturing processes, yeah, along the complete process chain in the car body manufacturing. Yeah. When we go, I will show you, let's say, also not go too deep into different applications, but give you an overview. So the first, I will do it in the form of case studies. And the first one will be a sort of geometric measurement for inline. So when you see automotive production, You see here, this is the inner of an underbody, yeah? And here, the importance for the inline inspection in this, let's say, area of production is to assure later assembly. So the features that need to be controlled here have a function-oriented dimensions, because those are critical features which need to be controlled 100% on each car. And if any deviation to the defined tolerances which are detected to the line, then the line will be stopped, or it will be sorted out for immediate rework. Yeah? But also, as we heard in the presentation before, it is, how to say, better not to stop the line. That means with some statistical analysis, you can even recognize trends in your production, yeah? And then you can give a trend alarm, and even before a failure occurs, you can optimize your production processes, and you can also do some predictive maintenance on your production. Yeah? And you have seen here the holes. One sort of sensor which is doing this, we call the so-called IMAX Cloud. This is a very compact sensor which can reach different areas at the car body. And this is then really, how to say, for measuring features like holes, like slots, like also like rivets. And I think I will show you now a real video out of automobile production. And then we will hear how the customer is also working with the sensor. This is from the production of Volkswagen in Poland, where they are doing the crafter production. Yeah? And I think we can go now into this movie.
The VW Crafter is manufactured at one of Europe's most cutting-edge production facilities. 100,000 Crafter vehicles available in 60 different versions will roll off the production line at the site in Września, Poland, which opened in 2016. Quality assurance is crucial, which is why the site has a state-of-the-art measuring lab. Here, the robot-controlled Zeiss AI Max sensors are programmed by VW engineers for use in production. The AI Max sensors combine 3 optical inspection methods for measuring complex geometric characteristics, including special boreholes, holes, screw threads, gaps, and flush. VW opted to leverage these benefits at multiple locations in the production facility. We're using 5 optical systems here at our site in Września. What is so special about this setup is that we have inline systems performing 100% inspection in production, as well as an offline station in the measuring lab where we write the programs without interrupting the manufacturing cycle. This way, I have enough time to optimize the programs and then transfer them to the inline stations. And it's just like Windows. All it takes is one click. Once this is completed, the programs from the measuring lab are used at the inline stations to check every part, from chassis or side panel all the way to the car body. This ensures process reliability throughout the production cycle. The sensor we use is really compact. Although it contains so much technology, the sensor head is quite small. It even features extra illumination, enabling us to measure pressure bolts. That isn't possible with other sensors. And we're able to access different areas of the car, including the interior area and difficult to reach corners. This makes it very effective. However, the system does more than just monitor the strict VW quality standards. The advantage of the system is that we don't just measure geometry, we also see it in the form of photographs. These are being taken constantly. To take just one example, these photographs allow us to inform the operator that there is too much glue on a mounting hole, which can then be adjusted. This is a lot faster than the proverbial 1,000 words or an email, and it's also a really practical method for visualizing defects in a way that's clear and comprehensible.
Okay, thank you very much. So I think this was, let's say, Okay, going on here. We will now show you also, let's say this was one sample from the Volkswagen Crafter production in Poland. And my colleague Uday Dixey will now show you also some applications which we are doing directly in India, to show you also some specific references from India. And
yeah, thank you, Michael. Thank you for a nice introduction. So we are wondering whether this can be used only for automotive application, or is there any other industries where this technology can be used. So we would like to show you some videos for other application. You can run this video. Yes. Yeah. So one industry is fabricated industry. Here we have shown an example of a motorbike frame, where there are around 30 or 40 brackets are welded, and presence and position of each bracket or each element is very important before it goes for assembly. So you can ensure that everything is perfect as per the design and no production time is lost just because there is one bracket is missing, or one hole is misplaced, or one bolt is not straight. So everything can be avoided by not sending a wrong part into the production line. So you here again we have shown an example of AI Max Cloud sensor, which actually digitize the whole feature and capture a point cloud data. So the results are much more clear, and the quality of the inspection is highly reliable. As you can see, even a small thin cross section of a pipe, it can also be captured here. You can see the quality of the point cloud data of various hole position. Even if you want to see if the threads have, if there are threads inside the bolt, or if there are spatters inside the bolt, which could cause some assembly problem. So this also can be detected very easily. Whole system can be installed right on the shop floor, and the black artifacts, as you see here, can take care of the temperature variation during the day, and the results will be very, very reliable throughout its inspection cycle.
okay, we go to the next sample.
Yes, yeah. Now another example could be small sheet metal parts, stamp parts, which also goes into various assemblies such as white goods products, and you want to see whether each and every operation is done before it goes for assembly, and it can also be detected. The results can be superimposed on a CAD model for a very simple understanding. Of course, you can also have a complete process control. For example, if some hole is getting deviated slowly, you will get warned before you produce a not okay part, and you can take a corrective action beforehand. Another example could be a casting part. Yes. Yeah, now before you send this part for the machining, you want to see whether everything is within the tolerance and you don't have anything missing or less material, so that you are not losing money in the machining process. So 100% inspection would be possible right on the shop floor with the reliability. So besides automotive, we showed you application in the fabrication industry, stamp parts or press part or casting parts. Over to you, Michael. Yeah.
Okay, thank you. Now we come to one application, which is called the case of application, flush and gap application. So this is now a case where we are, let's say, really looking for the importance of quality perception. There is quality perception where, for example, the customers all of the world in the meantime, they have an extreme awareness for perfect flush and gap dimension. And this is also seen like a sign for quality of the whole production. But of course, there are also functional requirements, like, let's say, a good gap is important for the tightness of the vehicle. Also, let's say, therefore, we have seen also in the VMT presentation the sealing performance. And then, let's say, it is important for door closing effort. This is also some perception how a door is closing. And of course, let's say, driving and wind noises are, let's say, important functions which is assured by a good flush and gap. I will show you, let's say, flush and gap is typically, how to say, performed in different areas in the car body production. So we have the necessity to control this in the body in white area. We have also the necessity to control in paint shop and in the final assembly. One reason is that each department wants to sell his part to the next department, and it should be okay. And also, let's say, what is also important in a smart factory is to combine the measurement data which you have derived in body in white, in paint shop, and so on, in one central database, that you can, if something happens, also derive some failure analysis or the origin of failure. This is also done by different sensor variants. So there is, let's say, thin sensors which are pretty, how to say, beneficiary also in price. Let's say for the IMAX here, we can use the Zeiss IMAX Twin, which is measuring geometric gap on flash, on painted, and also on metal surfaces. And we have one sort of sensor, the IMAX Twin UV, which is able to measure even on glass or, let's say, transparent surfaces. I will show you one sample. This is from the Opel factory. And there you will also see something, let's say, what we have also seen in the presentation before. And hello. Now it comes. So we see here the flush and gap measurement at Opel in Rüsselsheim. And also you see here one technology package which is important because we have a line that is not stopping. So there is a continuous flow of the car. And here we have to do the measurement with alignment of the car, with the position recognition of the car, that the robots can follow the car at, let's say, to measure at the reasonable positions for each flush and gap measurement here. And here you see the car on a skid. Sometimes the cars are also freely positioned on a, how to say, on a transport belt. And we will see in the next technology presentation also some collaborative robots maybe doing this also, let's say, when people are around. Then, let's say, these are the results which are typically then, for example, visualized in the next station, that the workers can do some, how to say, rework or specific rework on the parts where they have seen some failures. Another important inspection in the automotive industry is surface inspection. This is also a matter, how to say, where we are having the quality perception of a car. And here we have the situation like we heard today. It is important to detect a failure as early as possible in the process. Because at the beginning, when you have, for example, stamped parts, they are costing only €1. If they have a crack or any defect, to throw them away is very cheap. When you are more further than in the, how to say, in the already pre-assembled or complete assembled car, and you will find a failure, then it will get very expensive to do any rework, or even if you have to throw away the car, then you have very high damages. And what you're seeing here also, let's say, when you have a surface defect on a metal sheet, it is very difficult to recognize this. Of course, the people have technicians to detect them with grinding stones, but this is also time consuming. After recoating, e-coating, you will maybe see a little defect, but latest when the car is completely painted, then such a, how to say, defect surface will become very obvious to the customer, and then let's say you have really a problem. We have nevertheless also solutions, and I will show you in this screen, where we are doing surface inspection here as the sample of a complete car body at a mini production, where you can see how this is done. I will just show you here the first cycle. So the car is coming on the transfer bed into the measuring station, and you see here that 4 robots equipped with an ABIS sensor, which is specialized only for surface inspection, are going very fastly over the car and inspecting those areas which are very important for the customers. Because if here are any defects later, how to say, it is very visible for the customers. And so you hear the complete car body for the visible areas are inspected very fastly. And then typically after this station, you see here there is still some manual work, but after that station, the car is mainly sold to the painting area and is going to the next department. So another sample what I want to show here is then complete surface digitization. So here we see a offline robot station from GOM, yeah, where we are measuring complete parts by complete digitization. Yeah. And why we are doing this, I think this is very interesting to get really a digital twin of the part, and also doing virtual assembly of digitized, for example, hang-on part, really to look which hang-on part is fitting into the sidewall of the car, and then you can do, let's say, the perfect fitting of the measured components to that car. Yeah. Of course, you have also some process monitoring. What we are doing currently here at ZEISS is also to put this offline station into the line. Yeah, you see it on the right picture, where we are preparing those robots or empowering these robots for the 100% inspection in the line. Why is it, how to say, interesting to have 100% inspection? For example, you can do time-lapse analysis of a component. So what you are seeing here is when you measure on each part, you can really see how the failures are, let's say, how to say, going over the time. Yeah. And so this is a so-called heat map or weather map, where you see really, let's say, the deviations over the time, and you can see maybe 4 failures in the pressing, in the stamping department, where failures are coming from, and where failures are maybe, for example, going over the time, in what direction. So you see different, let's say, items that can be evaluated, like the range, like the mean value, like the variances here. Here you see currently the ranges of a failure over the time. Yeah. So just as an impression, as we are short in time, I will go to the next slide. What you see here is, let's say, that is very, let's say, not only about a measurement, about machine vision sensors. You need also, let's say, to collect those data in a, how to say, central quality database, where the customers can how to say, supervise the quality data from their production, but also, let's say, from different suppliers or even, let's say, from other plants. Yeah? So in a central database like PyWeb, yeah, you can, how to say, really do the visualization, and we will see it here. You can collect data from inline measurement, from outline measurement. You can also collect the data from non-size devices, and you can even collect the data from manual measurement devices and also from the process to have really a comparison of what, let's say, a picture what is happening in the production, comparing different results. And I show you in this picture, there you have really, for example, a picture for correlation for inline and offline data, but this is also representative to look, for example, to make analysis, how the change of process parameters may have an effect onto your production, and then you can make those, how to say, correlations between process parameters and also, how to say, the outcome of the production visible. So what we are seeing here is some sort of really the necessity to transform measurement data into meaningful results. So we have seen the, let's say, three main pillars, the areas, let's say, for flush and gap, ABIS inline, surface inspection, offline inspection. And also we have currently a trend of, let's say, not only inline inspection, but also bringing metrological accuracy into the processes. Yeah, I think this is the next step in metrology, that you're not only that you are, let's say, decreasing the effort, for example, for CMM room, because you can do metrological correct measurements in the line, in the production line. And here, this is my lead out. We are doing those here in Neubeuern, in Neuenstein, in Braunschweig, where we have dozens of robotic measurement cells to empower robots for metrology and inspection. So thank you very much for participating. And if you have any questions, you can give your questions to us. And yes, that's it for the moment.
Thank you, Mr. Scheffler and Mr. Dixit. Thank you so much. I'm sure the audience will have more questions, and we request the attendees to kindly put your questions in the chat box to us. We will collate the questions, and Mr. Nath would do the moderation in the end for the Q&A. We'd like to now welcome Mr. Peter Weiklund and Mr. Pawan Raika from LMI Technologies GmbH and Geoinformatic Consultants for their address on collaborative robots enabled with 3D vision for inspection applications. Over to you, Mr. Weiklund and Mr. Riker.
Thank you. Thank you. Good afternoon, everyone. I'm Peter Weiklund with LMI Technologies. I'm Senior Business Development Manager, and I'm here together with Mr. Pawan Raika, Technical Manager of Geoinformatics Consultants of New Delhi. A little bit about LMI Technologies. It's a Canadian company. We are headquartered in Vancouver, British Columbia. The LMI Technologies was actually formed back in 1998 by 4 sensor companies coming together. So we have more than 50 years of experience in making sensors for industrial applications. We are today more than 300 people working in 11 different office locations around the globe.
Right, so we, Geoinformatics, is an Indian organization. We having the offices in Delhi, in the north part of India, and then we having Bangalore and Chennai to cover south part of India, and we covering west part of India from Pune location. So Geoinformatics is a collaboration with multiple industrial organizations to provide technology to India. We have almost installed and commissioned more than 500 hardwares in the country, along with more than 100 software licenses for various sectors, mainly automotive, and we have sub for aerospace and government organizations as well. We do have separate division for automation. We call department as smart. So there we give solutions with embedded with the 3D vision machine systems to make your current process easier, smarter, and more efficient. Over to you, Peter.
So robots have been used for decades in industrial manufacturing applications to perform tasks such as welding, part picking, metalworking, etc. But without vision systems to guide robot movements and actions, these applications were limited to performing the same or very similar operations over and over on precisely located parts. Consider an application where 5 similar but not identical sets of parts need to be welded. Without the vision system, you may need up to 5 robot stations to do this. With each part must be mounted in a high precision fixture and then welded by a tool attached to a robot arm that moves with high accuracy and repeatability. When a vision system is paired with a robot, one welding station can weld all 5 part types, as well as other parts. Each part doesn't need to be manually and precisely mounted. The robot will move to a predefined starting point, with the vision system then aligning the parts as required. Low contrast objects, that would be typical objects like lettering or symbols on a tire sidewall. You would have a black letter on a black background. That's something that a laser sensor or a 3D sensor easily can pick up. Using lasers and bandpass filters, that makes the sensor perform well in varying lighting conditions. Pre-calibrated means also that the the sensors are temperature cycled and they are calibrated in the total measurement range and the field of view to give excellent measurement results in engineering units within a defined temperature range. LMI produces mainly 2 different sensor types: laser triangulation and structured light. Laser triangulation is typically the preferred option when the object is moving or the sensor is moving over the object. And when you use structured light, it's important that both the sensor and the object are stationary. So when you have a sensor mounted on a fixed frame looking into a bin, some sort, or a place of operation, you can have that sensor report positions of parts to be handled by the robot to the robot, and the robot does this. For instance, when you put a sensor over a belt and measure in bin picking here, different parts, you convey parts to the robot to be picked and be put on a second conveyor, for instance, sorting. Or the sensor actually is fixed mounted over the belt here, and the robot picks the sensors as they, or subassemblies as they come, and puts them in the right orientation in the second row for further processing. We've also heard of inspection and the importance of inspection with fixed sensors. That means that the sensor is mounted on a frame and the robot actually puts the workpiece in front of the sensor for checking that the part is correct. Here we can symbolize it with just putting a dice in front of the sensor here, rotating the dice and taking snapshots of each side. And then you get the fully inspected part, for instance. Second application, or another automation optimization application, would be to measure pies or pastries as they come down on a conveyor. They can be of varying height, varying diameter, and not 100% in the same position all the time. So the sensors is fixed mounted over the conveyor, measure each pie and reports position, height, and diameter to the robot that actually cuts them into the correct sizes. Over to you, Tawan.
Okay, thanks, Peter. Thanks for the information. I hope Peter and my other colleagues, other speakers, have shared a lot of information how the vision can be combined with the robotics and can make your entire robotic more efficient and more better in terms of performance. So all these kind of sensors or 2D vision cameras or 3D vision sensors act like an eye to a robot. Generally, robots are programmed in a way to move to a particular location and move to a particular location. But if you're adding a vision camera or 3D embedded sensors, this can give a real-time dynamic feedback to your robot and can make the things happen in a better way. In this way, you can save a lot of cost of making expensive jigs and fixtures, which is guiding the robot to pick the part from the particular fixed location. Because of the vision systems and 3D vision systems, your robot can now take the dynamic feedback and can have that freedom to, even if part is not at the very precise location, it can still pick it very accurately and then place it on a very particular location. Next slide, Peter, can you go to the next slide? Yeah, so here we are mounting a roof on the BIW of a car. So generally for this application on a running line, the car doesn't going to stop on a very precise location. So currently, the current process, the operator manually assure that the robot at the end is exactly placing the roof on the car body or not. But here in this slide, you can see we're using a vision systems which are giving dynamic feedback to the robot controller and robot adjusting its current coordinate and poses so it can place the roof exactly where it is required. This making the entire process fast and more efficient. You can go to the next slide. Here is a small video. So here the customer wants to place this cap over a pipe. Now this pipe having a large diameter with a very thin walls. So and when the pipes are coming rolled down, they doesn't stop on a particular location, and their orientation also varies. So robot need to be guided properly so this cap can be present exactly on the pipe. Now what we're doing is using a 3D laser profiler which scanning the pipe and giving us a 3D point cloud data. So with the help of this point cloud data, our sensor is directly sending the pose information to the robot, which having the X, Y, Z coordinates along with the orientation information. So robot will go and exactly put the cap without any human intervention in between. We'll go to the next slide, Peter. So either the part is stationary, sensor is stationary, we can keep the part stationary and sensors moving with the help of a robot or with a sliding gantries. We can inspect the part and we can place it, or either we can do either way. The part is stationary and the sensor is moving, or sensor is stationary, part is moving. We'll go to the next slide. Here we showing some very common application in the automobile industry like welding. So after welding, you need to verify that there's no welding is missed or the weld quality is proper or not. Earlier, like because this is a very small area, very small precise location, you need to do welding. So robot need to be programmed very accurately and without use of jigs and fixtures. That is not possible if it's changing model to model. But when you have a guidance, live dynamic feedback from a sensor, it allow your weld torch to move on a very specific path, and without any additional fixtures or jig, you can use the same welding robot to do the welding on various different kinds of models. You don't have to prepare jigs and fixtures for each model when you make it. We'll go to the next application. Here we doing a glue bead inspection, glue sealer inspection. So again, the robots go to different location and verify that there's no glue is missed, and glue will be having is a proper height and width. If any glue is missed, just give the dynamic feedback to the robot, so robot can go and exactly dispense the required size of the glue. And this, because it's a real-time feedback, so on the production flow itself, you'll be able to control the quality. You don't have to inspect on the later stage. We'll go to the next slide. Other than that, we have area sensors which can scan a logo or a particular area at a time, which can allow you to verify the position. For example, here the logo of the vehicle, we can verify the position. Not only that, we can also do a OCR, which can read these character and verify the required string is present or not. As this is a 3D sensor, so advantage of the 3D sensors are they can not only do the X and Y, but they can do Z also. So you can measure all those depths and height present along with the verification. And as I said, all the time the live feedback is going back to your robot controller or to your PLC. So you can continuously monitor your process. We go to the next slide. So our sensor Gocator, we call this as a Gocator, we call this as a smart sensor. So why call this as a smart sensor? Because it not only scans, it processes the data and it has inbuilt measurement capabilities. Us, it is certified with the UR, so we have direct plugin available for UR. You can directly plug and play with the sensor. We also provide a support sample file, so sensors can be integrated with Yoshikawa, Techman Robot, KUKA, and Fanuc and ABB as well. So almost all leading industrial robots, we can do the direct communication without the PLC in between. It can communicate to a robot and can provide a real-time dynamic feedbacks in a real-time format. Next slide, Peter. So all in one is, again, we call this a smart sensor. It not only just measure, it scan, means it captures the data, it control, it process the data. So you're not putting any additional controllers to process the data. Then it also has a measurement capability. It's a simpler browser based thing. You plug in, open any browser in your system. It may be Chrome, it may be Firefox. You can set up a simple measurement tools like diameter or robot pose or distance or height, and you can feed it tolerances, and it can send you the direct digital output on your PLC or on your robot. So that digital output as a value or as a decision can be taken. So it can directly give you 1 or 0. Okay, this part is okay, do this process. This part is not okay, do this process. Beauty with the 3D sensors are they are not dependent on ambient light conditions. When we're using a 2D vision camera, you need to take care of lighting condition. The ambient light is okay. If it goes too bright or too dull, you may not get the good data. But when you use a 3D vision system, you're not depending on the lights. Let your shop floor be too bright or too dull, your sensors is able to capture the good quality of data and give you the exact measurement result which is required. Then again, these sensors are smart because they are not required all the time the PC to do any measurement. You can write the logic right inside the sensor and later let the sensor work. So those algorithms measurement features are present within the sensor. So it can do all those measurements required and directly send us a digital output. Go to the next slide. So we'll conclude on the link on the top. You can see there's lmi3.com virtual smart sensor. So you can go to that link and you can virtually get a lot of scenarios we have made where you can see the data of a various, it may be a automobile part, it may be an aerospace part, it may be a packaging industry part. So you can try yourself by this, and even you can contact me or Peter on the given email addresses. We can help you out. You can use these sensors, you can try yourself, and you can see how easily we can create a program. Even an operator level guy can come and simply drag and drop, create a logic, and done. You're good to go. Plug and play and done. So that's why I conclude our presentation over here. Thanks for your time and listening to us. Over to you, sir.
Yeah. Thank you, Peter and Pawan. Thank you very much for the presentation. Interesting presentation, friends. We had, I think, 3 very interesting presentations with a lot of applications. May I request the other speakers also to kindly switch on your camera? We'll quickly. Time is running out, but maybe quickly we will like to put some questions which we have received from the audience. Let me start with Dr. Klenkels. Dr. Klenkels, the question for you is, how easy or difficult is it to integrate robots with image processing? And part is, what expertise is needed in terms of maintenance?
That is a question which I can firstly answer with, it depends. So if you have a very easy task to do, it is like Pawan said, an operator level possible approach. And we follow a philosophy and paradigm that says everyone who bought the system has to be able to extend the system to its needs, to adapt the system to its need, and to get stuff repaired if something happens. So no programming, just configuring. We have to divide systems into, is it a classical 2D vision system with teaching in patterns? Or is it an multi-dimensional inspection system with 3D and color and data matrix code? So it depends. But the crucial point is training, knowledge transfer. That is at VMT over the overall goal. So we have certain training programs where we transfer our knowledge, our expertise or special applications into the brain of our customers with training, with hands-on on their own system running in their processes. That everyone after that is happy to use the system, because our phrase that we follow is, if the operator isn't happy to use the system and isn't able to extend and repair and change the system, you won't sell a second one, you only sell one. And that is not our approach. So transferring the knowledge to the people, that they are able to deal with their own stuff, then that is the overall goal.
Right. Thank you, Dr. Kleinkes. Coming now to Mr. Scheffler and Uday. What is the cycle time for inspection? And the second part is, can the system be used offline mode, or does it have to be inline system?
Okay. The cycle time, we have seen this feature measurement. So typically when the robot is moving to one position, taking the picture and then measuring, we are about, let's say, between 2 to 2.5 seconds for each measurement of each feature. Of course, when you then have a certain area, then you can also measure multiple features in one area of the sensor, especially on the point cloud. Then you have a multiple feature measurement on one shot. Yeah. And the second question was if we have also offline cells, of course.
Offline mode, or does it have to be inline? Yeah.
Yeah, so not all stations are, of course, inline, yeah, because sometimes you want to have an offline cell, you want only to make some sample inspection where you are getting out 3 parts per hour to such a cell, and there we have also offline cells for those. Let's say, if of interest, I have just one picture where I could show, just as a sample, then you may shortly share the I can share the screen.
You want to share the screen, Mr. Scheffler? Yeah.
For 1 second, then you have one impression of such a cell.
Okay, please go ahead. Yeah, quickly. Yes.
So, do you see this cell?
Yes.
Yeah. Right. So this is just a sample of a small cell which you can put offline, which is also some sort of transportable in the, how to say, construction site, where you can put such a cell to a certain area in your construction site, yeah? And then you can have different strategies of feeding your part into the cell manually, or also with some sort of automation. Yeah, this is possible. So that's all I would like to show here.
Right. There's another question that has come just now, Mr. Scheffler. I think maybe it is relevant for you. Is it possible to check the dimensions of the machine block, and what will be the accuracy level of the inspection? Whether we can get the dimensional report for each parts?
Yes, I have shown, let's say, I start at the end. When you have a reporting tool like PyWeb, we have also some, how to say, smaller reporting tools here. Then you can really do, how to say, a reporting on the parts you have measured. So.
Right. Then I would like to come to LMI technologies. Peter, there's a question. How much response time impact and robot speed due to real-time sensing? Not sure. Is it clear, the question?
I would say that sensors are, in general, they have different speeds. Like a laser sensor is generally a very fast sensor. can run with several kilohertz and have very short latencies. A snapshot sensor will have to output multiple frames to be able to build up a 3D point cloud. So it's very, and that may take up to a second or 2 seconds. So it's very, very different. And I think when you use a laser sensor together with a robot, the laser sensor will never impact the speed of the potential or the possible way of inspecting something. But with a snapshot sensor, during the exposure and the capturing of the data, everything must be stationary.
Okay.
I hope that answers.
Yeah, earlier there was one more question, Peter and Pawan, maybe you could take that up also. Is there experience of using robot with vision in the ceramic industry?
Ceramics meaning tiles. I think we have, yeah, we have experience with that. It depends a little bit on the material, because they can be very, very glossy materials, but generally it should be quite easy to do measurements there. I can't say on the top of my head where I have exactly applications.
I will add on to this, Peter. We did a recent project in India itself for the ceramic block inspection, where a medical industry want to inspect ceramic blocks where they are keeping their medical equipments. So they want an inline system where on a conveyor belt these ceramic blocks are passing, and the laser sensor should be able to tell them the width and height of those blocks. So the particular medical syringe or medical cutting surgical plates can be placed on those ceramic blocks. So we did this project with the sensor. So very much possible, I would say.
Okay, right. So I think you're referring more, Pawan, to technical ceramics. Those would be referred as the technical ceramics. Right. Thank you. Maybe the last question for today to Dr. Kleinkers. Dr. Kleinkers, will robots with vision system and AI, will they see an increase in application as we go ahead with the electric vehicle production, especially in India? India is very upbeat about electric vehicle production. So would robots with vision system and AI, will that get a boost if India goes ahead with the electric vehicle production?
Sound connection was not very perfect, but I got 80% of the question, I guess. So the core question, will robot vision increase parallel to India's electric vehicle? Yeah, it will, because what we see right now in the European market and what we see technically connected to robot vision and battery manufacturing, electric vehicle manufacturing, on the one side, electric vehicles are vehicles. So the production process of vehicles is a production process of vehicles, and it will still be, but the other part is they are electrical. So they have a battery, they have these motors are different. So the complete powertrain is different. And there are new robot vision applications. For example, 2 projects we are doing right now, that is replane inspection. So are there any alien items inside the battery? And when you plug in the battery modules in the housing, is there any item which is creating a disturbance that you have to find before you press in the battery modules? The second is the battery module itself and the container where the different battery elements are put in have to fit very exactly, because you squeeze in between temperature mask that is connecting the battery and the housing for temperature exchange, and that is a very crucial process. There VMT is providing systems to measure that part. So robot vision will increase because electric vehicles will increase and the demand for automation will increase, especially in India. India is, in my opinion, a country which has to catch up the technology pace that Europe and USA has in 10 years. We had a lot of time. We had the chance to develop over the last 100 years. But India is in a high-speed catch-up run right now, and that is like fast-forwarding the European industry and robot vision development in the next years. So it will not only increase, let me use the word explode.
Well, thank you. Thank you, Dr. Klinkers. With that, I think, friends, we would conclude the webinar today, and I would like to, on behalf of the German Engineering Federation, VDMA, like to thank, first of all our speakers, Peter, Pawan, Dr. Klinkers, then Scheffler, Uday, and my colleague Anna also. And most important, I would like to thank all our audience. We had a tremendous participation today, more than almost 200 people, and I was just trying to figure out the industries the audience came for would be interesting for our speakers also. Automotive, tractor and farm machinery, construction equipment, machine tools, food and beverage, pharmaceutical, steel and metallurgy. So as you can see, we had a really broad participation from the industry. I think the quality of the presentation certainly drew the audience and kept the audience intact. So thank you very much to all our speakers for their really nice presentation on a very relevant topic, I think, which has a lot of very significant for India. And also thank you to all our participants, and thank you for this opportunity that we could have this webinar with you. And with that, wishing all our friends in Germany and India a happy weekend. Stay well, stay safe, and thank you very much. Goodbye and stay well.
Thank you. Thank you.
Thank you.
Thank you very much.
Thank you.